This section is over buffer solutions. A buffer solution is any kind of solution that will resist a change in pH when you add either an acid or a base to it. Our blood is a good example of a buffer solution. If small amounts of acids or bases are added to our bloodstream, our blood resists that change in pH, which is really beneficial for a biological system. You want to keep its pH pretty close to a specific number. Buffer solutions are solutions that contain either a weak acid and its salt or a weak base and its salt. They can also be composed of weak acids or weak bases, although you probably won't see that as often. The first thing you want to be able to do is identify whether or not you're dealing with a buffer solution. It's very common on multiple choice questions for them to give you a bunch of solutions and ask you which one's the buffer. So let's take a look at an example of this. Here we have a weak acid, acetic acid, and we have a salt made from the anion of that weak acid, sodium acetate. So this is a great example of a buffer solution. Here we have a strong acid and its salt, so that is not a good buffer solution. Here we just have two salts, so also not a buffer solution. Here we have a weak base and a salt from that weak base, so this is a good buffer solution. The way buffer solutions work is you have that reaction where you have the weak acid and its conjugate base, and if you add a little bit of hydroxide ion to this, the hydroxide reacts with the acid to create more of the conjugate base. The overall hydrogen concentration doesn't change very much. Or if I added an acid to this, the acid reacts with the anion, with the base, to create more of the HA. And so overall you have the reaction going one direction or another, but the pH itself doesn't change very much. The equilibrium expression for most buffer solutions can be written something like this. If we rearrange this just a little bit, we'll see that the value for hydrogen concentrations, and therefore the value of the pH, is dependent on the Ka, but is also dependent upon the ratio of the acid to the base, the acid to its conjugate base. And so if you have really large amounts of that acid and that conjugate base, then if you add a small amount of hydroxide ions or a small amount of hydrogen ions, the change in that ratio is going to be pretty small, and therefore your pH change is going to be really small. It's important, though, that you have large amounts of your buffer components and you add small amounts of your hydroxide or hydrogen ions. If you add too much hydrogen or too much hydroxide, then there will be a change in pH. There's always a point in which your buffer stops working. And here's the equation I was showing you earlier of the hydrogen ions reacting with the base to make more of the acid. Now, to find the pH of a buffer solution, there's a couple ways you can go at this. You can do this by going through and solving it the way we've always solved it, with ice tables, equilibrium expressions, the whole thing. Or you can actually use this magical equation here, the Henderson-Hasselbalch equation. This is the Henderson-Hasselbalch equation. It says the pH of a buffer solution is equal to pKa, that's a negative log of the Ka, plus the log of your base over your acid, right? Your anion over your HA. Alright, this is a different way to look at that. And as long as, if you look at this, as long as you have a specific buffering system made of very specific acid and base, acid and conjugate base pairs, as long as you have the exact same ratio of base to acid, you're going to end up with the same pH. Now, this equation is really awesome. It works great, and so students like to try to use it for everything after they get used to using it. Be real careful with this. This equation can only be used for buffer solutions, and you have to know what the acid and base are to be able to use it correctly. So to summarize, your buffer solutions have to have pretty large concentrations of the weak acid and the corresponding weak base. If you add hydrogen ions, they're going to react with the weak base. If you add hydroxide ions, it's going to react with the weak acid. The pH is determined by the ratio of that acid and the base, as well as the pKa, so also the Ka value. And the pH won't change very much as long as your concentration of your buffering materials are pretty large compared with how much hydrogen or hydroxide you're adding to it. So let's take a look at a reaction dealing with a buffer solution. Starting out, these are going to look pretty similar to what we've done before. There's just going to be a little bit of a difference here. I'm going to show you how to solve this two ways. I'm going to show you how to use it, how to solve it using an equilibrium expression, and how to use it using Henderson-Hasselbalch equation. I'm going to blow this up real big so that I can fit my work on here. So starting out, we're going to start with our balanced chemical equation. And it gives us in the problem the molarity of the lactic acid, 0.12 molar, and the molarity of the sodium lactate. This is lactic acid, this is sodium lactate. It takes out the spectator ion, so sodium's not there, but the anion, the lactate anion, is still present. So when setting up our ice table, those are our initial values of these substances. Since there's no hydrogen concentration, that means this reaction cannot proceed to the left, so it's going to have to go to the right. And so our changes are going to look like this. And since we have a low Ka value, we're going to go ahead and make that assumption for our equilibrium values here. Once we have this, we can plug it into our equilibrium expression using the Ka that was given to us in the problem. And if we solve for x, we get 1.7 times 10 to the negative fourth, which is equal to our hydrogen concentration. And once we have that, we can use that to find pH. So if we go through and solve this, we get a pH of 3.77. Now I'm also going to show you how to do this using the Henderson-Hasselbalch equation. So I'm going to move this over here, and we're going to do the same problem again using a different equation. Okay, here's our Henderson-Hasselbalch equation. Our pH is equal to pKa. That's going to be negative log of our Ka, plus the log of our base concentration over our acid concentration. And this is going to be equal to our equilibrium concentrations of our acid, that's that one, and our conjugate base, that one right there. So this is our setup here, and be sure that you're trying this on your calculator as well, so that you can be sure that you're getting the right answers here. If we go through and solve this, we get a pH of 3.77, which is the exact pH that we got over here. They're exactly the same, so it doesn't really matter which way you solve this, you're going to get the same answer either way. We'll take a look at another buffer problem together in class. Two terms we need to be familiar with are buffer capacity and pH range. Buffer capacity is pretty much how much acid or base these things can absorb before their pH starts to change. Now what we saw before was the pH depends on the value for Ka, but it also depends on the ratio of the base, the conjugate base to the acid. The capacity, the buffer capacity, depends on how much of the base and the conjugate acid you're using. So for example, if I have two different solutions of an acid and conjugate base, but of different molarities, if I had this solution here with 1 molar amounts of both the acid and the conjugate base versus this solution here with 0.1 molar amounts of them. They both have the same ratio of conjugate base to acid, so they're both going to have the same pH. However, since this guy over here has a lot more of the base in the acid, it is going to actually be a much better buffer. So I'll be able to add a lot more hydrogen ions or hydroxide ions to this solution before its pH changes. This one right here is not going to be as good a buffer solution. The pH range of a buffer solution is going to be the range over which a buffer works pretty well. All different buffer solutions have different pH ranges, some are around 7, some are around 5, some are around 9. The way that you make a buffer, if you're asked to do that, is probably the best way to do that, is to make sure that the concentration, the ratio of the concentrations between your acids and your bases are the same. In other words, you want to make sure that the ratio of conjugate base to acid is going to be equal to 1, in which case your pH will equal your pKa. And when that means that you want your pKa to be as close to the pH that you're trying to get to. So you want your pKa to equal the pH range you're trying to accomplish. You're also going to have the best buffer if you have large concentrations, large amounts of the acid and the base. So here's an example of two different solutions. Solution A, in which the ratio of acid to base is 1. You add a little bit of something to it, the pH only changes by 2%. And in solution B, the ratio is not 1. You add a little bit of something to it, the pH changes by 50.5%. So our best buffers are ones that have large concentrations, are ones in which the ratio of the acid and base are 1, and ones in which your pKa is close to the optimal pH range. Solving buffer solution problems don't have to be incredibly hard. Usually the problems will break them up for you to make it a little bit easier, so that you're dealing with an equilibrium problem and you're dealing with a buffer problem. You can make use of Henderson-Hasselbalch if you want to. There's a lot of different ways to solve these problems. Let's take a look at this last example. Here we have a buffer solution made of acetic acid and sodium acetate, and we're going to be adding a base to this, which means that our equilibrium expression is going to look just a little bit different than it did before. Remember, when you add a base to a buffer solution, the base reacts with the acid, so we need to show that in our equation. And now the hydroxide ion is going to react with the acid to make water and to make our conjugate base. Once you've got this, you can set up your ice table and start putting in your initial amounts. And in buffer solutions, you assume, and this is important, you assume that all of the hydroxide ion or all of the hydrogen ion, depending on what you're using, gets used to completion. So that means we're going to use up all the hydroxide. And then after we've got that, we can solve for our equilibrium values. Now after I've got to equilibrium, probably the easiest thing to do, since I've got acid and conjugate base values, is to use a Henderson-Hasselbalch equation. Now in this problem it doesn't give us the Ka, but when we had initial values of this and this being the same, its pH was 4.74, that means its pKa is also going to be 4.74. And then we can plug in our base and our acid concentrations, and we get a pH of about 4.80. Something that's interesting about this is we started with a pH of 4.74. We added 0.02 moles of NaOH, and our pH went up by 0.06. If you add 0.02 moles of HCl, it'll go down by the exact same amount. It'll go down by 0.06.